Hi, today I'll talk about some reviews that we've learned before the nanoelectric technology. We've learned about the conduction band and the valence band, which means the valence band has some states that electrons could exist, and there are some electrons in it. But as the conduction band, there are some states, but no electrons living in the air. So by the valence band and the conduction band, we can separate the materials like instructor, semiconductor, and metal. Then we have learned about some toppings. When there is a silicon, uh, and we've topped as a fifth column of the atom. There are some electrons in it and free electrons living in there, and it seems like a negative charge, so we call that an n-type silicon. And in and when we dot that as a third column atom, then uh, there are some holes, so that means we can see that as a positive charge thing, so we call that as a p-type silicon. Then we've learned about the p-n diode, which is a connection of p-type silicon and the n-type silicon. And you can see as in the band gap, the junction part, as in the junction part, the Fermi level gets lower in the n-type silicon, which means there are some holes in it. There are much holes there are much holes, and in the p-type silicon, the Fermi levels gets higher from the valence band, which means there are some free electrons in it. The electrons and the holes in the junction area gets fixed and makes some depletion area in the junction area. When we pour some pass plus bias on the drain source and the minus bias on the n-type silicon, we can make some forward bias, and in the opposite we call that a reverse bias. But in the reverse bias there are some tunneling effects, so we can see some leakage current in there. Then we've learned about the MOSFET, which is similar to MOSFET, but there are no source and drain. Then we've learned about the MOSFET, which is the metal oxide semiconductor field effect transistor. We use this MOSFET as an amplifier and a switch. And in the MOSFET, we can see some graphs like here. When then the voltage gate gets higher, current the the current that flows in the source drain gets higher at a point of the gate bias, the gate voltage, the point which is the threshold voltage, which is a threshold voltage. And in the other graph, you can see that the drain source voltage increase. You can see the ID, the current that the current of the drain gets higher at the first time, but at a point it gets saturation. We call that point as a pinch-off point. Then we've learned about the CMOS, which we put an input a high, then we get a low, and when we put an input as a low, we get an output as a high. And then we've learned about the logic gates, which is made of CMOS. And then about the short channel effect, but we'll talk about this next week. And then we've learned about the SOI system and the multi-gate system and the FinFET systems and the memories. The SRAM has a 6 transistor in one cell, which means it has some difficulty in shrinking, but it has a high speed. In the DRAM, we have one transistor and one capacitor, so it is easy to shrink, but because of the capacitor, we should refresh this memory all the time, so which means it makes the device slow. Then we've learned about the flash memory. The flash memory has a floating gate inside the oxide and makes some floating gate in the oxide, which means there are one transistor in one cell, so it is easy to shrink. But in the flash memory, we have a hot carrier effect and a tunneling effect to move. Then we've learned about the VLAN, which is a 3D LAN. Thank you for listening, and thank you for listening.